This is mathheals.com, where you can find some more links to math YouTube videos and computer science. Let's take a look at a hypothesis test for a population standard deviation. And this is pretty well done by hand using tables and so forth. Better get my calculator going here. There is no TI-384 calculator functions really to do any of this. Get that. There we go. Okay, if a simple random sample of size n is obtained from a normally distributed population with mean mu and standard deviation sigma, then chi-square, that's what that symbol is. That's not x squared, it's chi-square. It's just notation. Doesn't mean the second power. Is equal to n minus 1 times s squared. S is our sample standard deviation, remember. N is a number in our sample. Divided by sigma squared. That's our population standard deviation. And has a chi-square distribution with n minus 1 degrees of freedom. Now, characteristics of the chi-square distribution. It's not symmetric. The shape of the chi-square distribution depends on degrees of freedom, just like the student's t-distribution. But as the number of degrees of freedom increases, the chi-square distribution becomes more nearly symmetric. And the values of chi-square are non-negative, so they're you're never going to have negative chi-squares. Now, requirements for you to use this. Sample is obtained using simple random sampling, and the population is normally disputed. Now, I've made up some problems, and I'm not sure whether I've actually said that those two requirements, but we'll run an assumption that they're true. Now, here's our classical approach. We can write down a shortened version of the claim. We come up with a null and alternate hypothesis, and H0 always has the equals part on it. See if the claim matches H0 or H1. Draw the picture and split alpha into the tails. And if we got a not equal to on H1, it's two tails. If we got a less than on H1, it's left tail. Greater than is a right tail. We'll find the critical values, and we'll do that using the chi-square distribution table. And then we'll find the test statistic. Now, I don't really like all these knots on here. It kind of gets confusing, I think, for students. But you can this is just test statistic. This sigma squared, sigma naught, what that's referring to is a number off of our claim, and we'll see that. If test statistic falls in tail, reject H0. If test statistic falls in the main body, accept H0. And determine the claim based on step 3. Now, I like to use reject and accept, but again, the accept isn't the appropriate word to use there. As an example, I had a student one semester in college algebra. She was an art major, wasn't very good at college algebra. Got 7-8% in every test. And this is the example I always use because it just kind of blew me away. Got 7 or 8% in every test, came in for the final exam, scored a perfect on the final. 25 out of 25. That's when there's 25 problems on the final exam. Almost unheard of. Maybe one person a semester gets that, and it's usually the top student. Well, I think she cheated. There's no way she came in and aced the final when she could barely do the simplest problems on the test. I mean, I understand studying at the end, but there's no way. I don't accept her innocence. Now the more appropriate way to write that is we do not reject her innocence. Now, that's different than accepting it. It just says we do not reject it. Because it's possible, isn't it? You know, it's possible she studied every second for the last 2 or 3 weeks and leading up to the final, and not that it matters. She still didn't pass the class. Getting a perfect on the final, the fact she scored 7-8% on every test, there's no way she's going to pass anyway. And then determine a claim based on step 3. Step 3 is see if your claim matches H0 or H1. Well, let's look at these steps. Okay. If ages of students at a campus are normally disputed with a mean of 20, now mean of 20, what they're telling us there is mu. Because it doesn't say anything about a sample at this point. And a standard deviation of 2.1. So that would be sigma. It is believed the standard deviation is lower now. That sounds like the claim. So lower than something. It is believed the standard deviation is lower now, so a study is done asking 15 students their age. Well, that means n is 15. It is found the standard deviation is 1.8. So this is referring to our 15 students. So this will be S. Test the claim at alpha is equal to 5%. Okay, that's what they give us. And here we go. Step 1, write down a shortened version of the claim. Well, I said lower than, and we have to figure out what value to put here. Since we're talking about standard deviation, we're going to put 2.1. The only values you can put up here are your population values. You can't put S, because that's a sample. The sample is used to prove or disprove this. Now, next step is to come up with a null and alternate hypothesis. It says H naught always has the equals part on it. How I teach this is for H1, the only symbols you can put there are less than, greater than, and not equal to. The only symbols you can put on H naught are less than or equal to, greater than equal to, or equal to. Now, our particular textbook we're using now only puts an equals on H naught. I really don't like that that convention. Because if you say this is false, and this is less than, and then this is just equal, you can't say that's necessarily true, because these are opposites of each other. Okay. Null and alternate hypothesis. Let me grab a drink here. So I'm going to have sigma on both of those. Okay, lower than. That implies a less than symbol. And H naught always has equals part on it. When I say that, I'm talking either less than or equal to, greater than or equal to, or equal to. Well, lower than, the only place I can put that is on H1. So I'll put that down there. Well, if this is a less than, then this will be a greater than or equal to, because these are opposites of each other. Now, step 3, see if claim matches H naught or H1. Well, we said this was a less than, and we put the less than on H1, so this matches H1. Step 4, draw the picture. Notice there's a less than on H1. Less than on H1 says we're going to have a left tail. Like that. Now it also says split your alpha into your tails. Well, alpha is 5%. We only got one tail. So I'll put the entire 5% in that one tail. Now all of this adds up to 100%, so if that's 5%, this has to be 95%. Now our critical value is what separates the tail from the main body. We only have one critical value here because we only have one tail. Excuse me. Okay. We did the picture, split our alpha. Okay, critical values. It says use the chi-square distribution table. Now we're going to need a degree of freedom. Degree of freedom is n minus 1. So n was 20. Wait a minute. Scratch that. 15. So 15 minus 1. Our degree of freedom will be 14. Let's look at our table. The chi-square distribution table. It's based upon the area to the right of the critical value. Well, here's my critical value. The area to the right of it is 0.95. Excuse me. We're going to look in the 0.95 column. We're going to look up degree of freedom of 14. So 0.95, degree of freedom of 14. And if my eyes aren't getting off, 6.571. And that's our critical value. Yeah. Okay. Test statistic. We're going to use this formula. So our test statistic is equal to n minus 1 s squared divided by sigma squared. Well, n is 15, so we've got 15 minus 1 times s, which is 1.8 squared, over sigma. Now, sigma is always a number that's off of your claim here. Sometimes it's given over here in a side, but it's whatever this is. Well, these are 2.1s, so that'll be 2.1 squared. Okay, let's see what that gives us when we plug in our calculator. So I got 14 times 1.8 squared divided by 2.1 squared. And how many decimal places? I have no clue. Let's take it to 10.29. Why don't I have a clue? It all depends. How close is it to your critical value? Because you're trying to figure out if it falls in tail or falls in the main body. So if it's real close to your critical value, you may have to take this out to 3 or 4 decimal places. Well, you have to think of this as a number line. Here's 6.571. Now 10.29, if that's a number line, falls over here somewhere. Don't know where, but that's where it falls. Then our conclusion. If test statistic falls in the tail, it doesn't. It's fallen in the main body here. So if test statistic falls in the main body, you accept H naught. Now H naught and H1 are opposites of each other. So if I accept H naught, that means I reject H1. Now, I say determine the claim based on step 3. Step 3 says decide which one it matches. Well, we said the claim matches H1. So whatever we say about H1 is what we're going to say about our claim. We rejected H1, so we'll reject our claim. And that would be our hypothesis test. Now, I look at this, lower than 2.1. Here's S, which is 1.8. And it's obviously lower than. But the key question is it's significantly lower than. So that's what they're really asking. If it was just, is it lower than, period, you can just look at it. But we're talking about significance, as if this is statistically significantly lower than. I'll learn to speak one of these days. Let's look at our second problem. Grab another drink here. Ate some garlic bread, and it's kind of killing me here. Guess that's what happens when you become 100 years old. Okay. If ages was, and I'm pretty boring here, I can't make up exciting problems. They're all the same, but I did change numbers and some words. If ages of students at a campus are normally distributed with a mean of 19, so they're telling us mu is 19, and a standard deviation of 1.3, so that's sigma, because they're not talking about the claim at all, or I mean a sample. It is believed that the standard deviation is different now. Different than something. So a study is done asking 22 students their age. So n is 22. It is found that the standard deviation is 1.9. So S is 1.9. Test the claim at alpha is equal to 10%. Obviously it's different. This is 1.3 and it's now 1.9. But is it significantly different? Well, we had to figure out what number to put here. And you always put population values here. We're talking about the standard deviation is different now. So we're going to go with 1.3. Again, you had to put population values here. And since we're talking about standard deviation, that's why I put the sigma. Different than, remember, is a not equal to. Okay, step 1, write down a shortened version of the claim. I did that. Do not get wordy on that. You're going to mess it up if you get too wordy. Just keep it nice and simple. Then step 2, come up with a null and alternate hypothesis. Well, the not equal to goes on our H1. And if that's not equal to, this has to be equals. So 1.3. Step 3, see if your claim matches H0 or H1. Well, our claim matches H1. They both have a not equal to symbol. Draw the picture. Not equal to an H1 says we're going to have two tails. Okay. It says split alpha into the tails. Alpha is 10%, and I got two tails, so I'll put 5% in each tail. Now, if I got 10% in my tails, that means I got 90% in the main body. Step 5, find the critical values, use the chi-square distribution table. We'll need the degree of freedom, which is n minus 1. So 1 less than n. N was 22, so degree of freedom would be 21. Okay. Let's find this one on the right first. So find this one. The area to the right of this is 0.05. So I'm going to look in the 0.05 column, which is right here, and I'm going to look up a degree of freedom of 21. Degree of freedom is over here, so I'll go down to 21. And we want in the 0.05. So 0.05, 21, I get 32.671. Okay. Let's look at this one. The area to the right of this one. You have to add up all the area to the right. So we add up the 0.90 plus the 0.05, which gives us 0.95. So I'm looking in the 0.95 column, and degree of freedom is still 21. So we got 11.591. Now, chi-square is always positive, so we don't make any of them negative. And those are our critical values. Okay, our test statistic. This is off of step 6 is equal to n minus 1 times s squared over sigma squared. Well, n is 22, so we got 22 minus 1 times s, 1.9 squared, over sigma. And this is just a number off of your claim. Even if sigma is not given over here, this is always just a number off your claim. So this is 1.3 squared. So we got 21 times 1.9 squared divided by 1.3 squared. And we get 44.86. How many decimal places? I don't know. Start with 2. See where that leads you. If they're nowhere close to your critical values, then it doesn't matter. Okay, here's the number line. Here's 11.591. Here's 32.671. 44.86 falls over here. It falls in the right tail. So our conclusion. If test statistic falls in tail, reject H0. Well, we'll reject H0, which means we'll accept H1. H0, our null hypothesis, and H1, our alternate hypothesis, are opposites of each other. If you reject this one, you have to accept this one. Now our claim, remember, matched H1. So whatever we say about H1 is what we say about our claim. We accepted H1, which means we'll accept our claim. Let me save this. And then we'll look at our last problem. Population standard deviation. Deviation, classical approach, page 01.pdf. There we go. Okay, let's look at our third example. I tried to come up with 3 examples to handle all the cases, the left tail, right tail, and two tail. I think I got one of each. Okay. If ages of the students at a campus are normally distributed with a mean of 23, so mu would be 23, because it doesn't say anything about a sample, and a standard deviation of 3.4, so that'd have to be sigma. Okay, it's believed the standard deviation is more now, so more than something. We're talking about standard deviation. Well, it has to be 3.4 because that's our population standard deviation. Okay. Study is done asking 12 students. So n is 12. It is found that standard deviation is 3.5. So S is 3.5 because we're talking about the 12 students. And it says test claim at alpha is equal to 1%. Okay, let's go through our steps. Write down a shortened version of the claim. We did that. Here's our null, and here's our alternate hypothesis. It says come up with a null and alternate hypothesis. H naught always has equals part on it. This is sigma. More than. Well, that's a greater than. And that would go on our H1. And if that's greater than, this is less or equal to. Again, our book, current book, textbook, puts an equals on this all the time, which I don't like. Because if this is false, then this would be true, for example. But if this was an equals, that isn't necessarily true. It may be less than. Now, I know you get the same result and so forth, but I just like how they match logically. Okay, step 3. See which one it matches. Well, our claim has a greater than on it. Here's a greater than, so it matches H1. It won't always match H1, but a huge amount of time it does. Step 4, draw your picture. Greater than tells it's a right tail. Here it is. Greater than, right tail. And we want to split our alpha into our tails. We only got one tail. Alpha is 1%. So we'll put 0.01 there. And if that's 1%, this has to be 99%. Because it all has to add up to 100%. Okay, find our critical values. Well, we need degree of freedom. Remember, is 1 less than n, so it'll be 11. And we're looking this one up. The area to the right of this is 0.01. So 0.01 and degree of freedom of 11. 0.01, degree of freedom of 11. 24.725. That's our critical value. Test statistic. N minus 1 times S squared divided by sigma squared. Well, N is 12, so we've got 12 minus 1. S was 3.5, so we got 3.5 squared. Divide by sigma squared, and sigma is just the number off of your claim here. So it's 3.4 squared. Okay, so we'll have 11 times 3.5 squared divided by 3.4 squared. Enter. 11.66. Start off with 2 decimal places, and then you can adjust it from there. It's nowhere close to our critical value, so 2 is fine. Here's a number line. Here's 24.725. 11.66 would fall over here. So for a conclusion. If test statistic falls in tail, well, this is the main body. If test statistic falls in main body, accept H naught. So that means we'll accept H naught. H naught and H1 are opposites of each other, so if we accept H naught, that means we reject H1. And if I look back up here, our claim matched H1. So whatever we say about H1 is what we're going to say about our claim. Well, we rejected H1, which means we're going to reject our claim. Let me save that. There we go. One last thing to mention. As you're working these problems, if S, which is a sample standard deviation, is not given in a problem, then you have to find it with one of the following. You'll be given like raw data. You'll have to use one of our stats on your TA3, TA4. And if you remember, to do that, you have to go into your stat, edit, input your numbers, do a second mode, exit out. Then you go back into stat, you right arrow to calc, I think it is. Anyway, you right arrow. And then one of our stats is your first one. And you press enter on it, and you press enter again, and SX is your sample standard deviation. Or if you're doing it by hand, there's two formulas actually. I just wrote one down here. Then S is equal to square root of the sum of x minus x bar squared all over n minus 1. And that's the end of that section. So I guess I'll stop the recorders here. There we go.